Hello, I'm Jeremy and I'm a product specialist at Abstract. In this video, we're going to look at how we can procedurally fill objects, such as this wooden crate, with different types of produce using InstaMAT's rigid body physics simulation capabilities. Now, at the end of this video, we'll have a reusable node that can fill any crate-like object with a large amount of smaller objects, such as apples or potatoes. You can then change the crate or the smaller object that we fill it with at any time, and InstaMAT will automatically generate a mesh with physically accurate collisions and no intersections. You can then use this node in other InstaMAT projects, or as a tool with InstaMAT's integrations into DCC applications and game engines. Now we've got a lot of fun things to cover, so let's get started. All right, so before we get started with our wooden crate, I quickly wanted to show you where you can find a simple tutorial project built into InstaMAT Studio that demonstrates how to scatter objects using physics simulations. So we're here at the welcome screen, and I'll just go and create a new project, and I'll click on Element Graph. And if we scroll down here, we can see we have the physics-based scatter tutorial. So I'll just go ahead and click that. And so you can see we have this really nicely documented project here. And if I go ahead and just show the viewport, we can see what this does. So all I have to do is go to the simulation iteration section here, and I can just increase this, and we can simulate these spheres and cubes on this plane, which is very fun and very cool. So now we're going to cover this entire process that we see here in this video. But if you're someone who likes to quickly dive in and adjust some parameters and deconstruct a node graph, then this tutorial project is a great place to start. So now here is a quick look at what we're going to be creating today. You can see we have this wooden crate, and we have a bunch of these apples that have been simulated and scattered inside of it. And so what we can do is I can go to the crate mesh input here, and I can change this to another crate, and we can now see, I can adjust the seed here. We can re-simulate this, and it automatically fills the crate with all of these apples. And, I can go ahead to the produce mesh input that we have here, and I can change the scattered mesh as well. So I can go to the potato, and we can now see that we're scattering and filling this crate with a bunch of potatoes as well. So let's go ahead and learn how to create this graph setup. All right, so here we are again in InstaMAT Studio, and you can see that I have this quick package set up here, and I've got a few meshes loaded into the package. I just dragged and dropped them into the package management panel. You can see I have a couple different crates, and I also have some smaller meshes like this apple, this onion, this peach, these different things that we can scatter and fill up our crates with when we do our simulations. Now, before we start working with these meshes, we need to create an element graph and set it up to start simulating. So let's go ahead and create a new project. We'll go to the plus button here at the top, go to element graph, and choose to create a project without a template. And let's name this element graph. Let's call it something like crate simulation, and hit enter. Now, right off the bat, what I'm going to do is bring in a node using quick search. So I'll right click to bring up quick search, and I'm going to type in physics. And you can see that we have this physics simulate rigid body node. And I'm going to go ahead and bring that in by double clicking it or hitting enter. Now, this is the node that does all of the magic for us. It allows us to accurately simulate scattering a bunch of objects with gravity and collisions. But you'll notice that it has some interesting inputs and outputs. The first thing it's asking for as an input is a point cloud. Now, InstaMAT uses point clouds to quickly perform simulations. Once the simulation is complete, we'll then spawn meshes onto the simulated points so that we can then see our results. Now, before any simulating happens, we need to create a point cloud. So let's go ahead and do that now. Now, there are a few ways to create point clouds in InstaMAT, two of which are with the point cloud shape generator and the point cloud from mesh nodes. So let's take a look at those now. So let me go ahead and find the point cloud shape generator and point cloud from mesh nodes. There we go. And let's view the output of the point cloud from mesh node, and we'll make sure we can see that in our viewport. And then let's supply a mesh. So I'll just go ahead and bring in something like our apple. And so right away, you can now see that we've created a point cloud using our apple mesh, and we've spawned a whole bunch of points onto the surface. And it's pretty neat actually, because we were able to get the color information for the points from the vertex colors of the apple mesh, which is pretty neat. And we can choose the component that we're spawning, that we're using to spawn those points. So I can change it to something like, the edge or the vertex. It's very, very cool, and we can very easily create great point clouds using this node. But we don't need nearly as sophisticated a mesh as this to generate our point cloud from for our case. So we're going to use the point cloud shape generator node instead to create some point cloud primitives. So I'm going to go ahead and delete this, and let's view the output of the point cloud shape generator. And so this node is really useful because we can generate some point clouds using some primitive shapes. So you can see I can change this to a box or a cone or a torus, for example. That looks pretty cool. But in this case, what we're going to use is the UV sphere. And so I can change, the radius, the segments of the sphere, and what component, of course, we're using to spawn our points. In this case, we can keep it 2 by polygon, but I'm going to change this to 1, so we only have 1 point per component, because right now we don't need nearly as many points for our simulation. Now, next up, let's start visualizing our 3D space a little more by enabling the grid. That's going to be the grid in our 3D viewport. And so this is going to visualize where the floor is in our world. So what I'll do is I'll click this 3D cube here to make it so that the viewport takes the center stage, and then we'll go to the viewport settings here. That's the gear in the top left, and I'll go down and find where it says show grid in the scene settings and just enable that. And so now we can see what we're going to use as the floor for our simulation. Now, if I go ahead and rotate around this, we can actually see that our point cloud sphere resides in the middle of our scene. So if we were to simulate gravity and collisions, only half of our point cloud would be simulated, and the rest of it is going to fall through the floor. So what we can do is we can move the point cloud upwards so that it sits above the floor and we can simulate our points. So I'll go ahead and make it so that we can see our graph in the center and our viewport here in the top left again. And to move the point cloud, we can use a node called point cloud transform. And so you see, if I click on that here, you can see we get some viewport gizmos. We can move this around. Let me just make sure I'm viewing the output of the point cloud transform node. And so now all I need to do, I can use the W, E, and R keys to position, rotate, and scale the point cloud. But let's just go ahead and use position, and I can just move this up above our floor. So I'm going to move this up pretty high, and I'm looking at my translate Y here, and I think somewhere around moving it up 1 unit, somewhere like that, pretty close, is going to be good for our case. So now that we've moved our point cloud up on the Y-axis, let's go ahead and connect our point cloud transform node to the input of our physics simulate rigid body node to perform the simulation. Now let's go ahead and view the output of the simulation node, and we can see that, well, we get a result that might be a little unexpected. It looks like most of the points from our point cloud have disappeared. Now, this is because when it comes to simulations, the scale and the density of the point cloud is important. And in this case, our point cloud is extremely small. If we go back to the point cloud shape generator, our radius is only 1 unit. So what we can do instead is I'm going to go ahead and view the output again of the shape generator here, and I'm just going to increase the radius from 1 to 10. And if I go ahead and hit F to focus again, we can see that we have a much larger radius for our point cloud sphere primitive. And now if I go back to the output of the simulation node, we can now see that we have a lot more points in our simulation. And so now what I can do is I can just go to the iterations here and just increase the iterations of our simulation, and we can now see our points simulating and falling down to the floor. Now, the reason why we weren't seeing our points before is that the physics node calculated that we had many overlapping points at such a small scale. And what this tends to result in is unexpected behavior with our simulations, such as the points, exploding out from the center at extremely high velocities, which in this case is not what we want. So what it did was it removed the troublesome points, leaving us only with a few to simulate. And then increasing the radius of our sphere gave our points much more space. It spaced out the point cloud, and the physics node didn't have to remove nearly as many. Now, before we talk a little bit more about iterations and time step, which are very important properties in our simulation, I want to add a few more nodes so that we can better visualize what's going on here. So I'm going to make some room here, or just kind of pan over, and let's go ahead and bring in the mesh spawn on point cloud node. And so this is the node that attaches meshes to each of our points in our point cloud. So what I'm going to do is just connect the output of our simulation and connect it to the input of our point cloud here, the mesh spawn on point cloud node, and view the output. And so now let's go ahead and change our view, and I'll go back to the simulate node and adjust the iterations, and now we can see our simulation a lot better. So you can see how this is going to be really useful when trying to diagnose what's going on with our simulation, as we can now visualize the collision shape for each of our points. So now let's go back to iterations and time step. The time step is how many milliseconds occur per iteration of our simulation. So you can see I have a time step of 50 milliseconds, and then if I set my iterations to something like 10, well, you can see not much happened here. And that's because our simulation is only occurring over 500 milliseconds, or half a second. Now, if I go ahead and let's increase the time step to like 100 milliseconds, you can see as I adjust the iterations that our simulation is happening very quickly here. It takes very few iterations to run the simulation. But if the time step is too high, then our simulation may not be as accurate. If I go ahead and now lower this time step to something like 1 millisecond, you can see that it's taking a large number of iterations, even just for the cubes to fall down slightly due to gravity. Now, lowering the time step makes our simulation much more accurate. You can see if I just adjust that here to 3 milliseconds to help it out, we can get this nice, fluid, smooth simulation. However, you can see that it's taking many more iterations to get our results, meaning it takes a lot more compute power to get our simulation to settle and resolve. So it really is a balance between these two. And in this case, what I'm going to do is let's just go ahead and reset this here. I'm going to keep my time step at 50 milliseconds. And then we're going to go ahead and adjust the iterations as we go throughout setting up our scene to get that complete, full, and settled simulation. So let me go ahead and just, increase the iterations here so we can get some of our simulation going. And right now you can see that we are simulating boxes. And we can determine, aside from, we can see boxes because we're spawning them using this spawn on point cloud node. We can see what our collision shape is for our simulation by clicking on the simulate rigid body node and going to the input collision shape here. And you can see we're using a box. And we have a whole bunch of other primitive shapes that we can use built into the node as our collision shape. Now, our apples are going to be more of a spherical shape, much more round. So let's change the collision shape from box to a sphere. And you can see that our simulation has now updated here. And if I go ahead and just rerun this, we can see that our boxes are now rolling around. They aren't falling flat on one of their surfaces because they're now using a sphere as their collision shape. But this doesn't really look right? Because we have boxes that have flat surfaces and they're just rolling over the surface. So what I can do now is I can change the mesh that we're spawning on here to something like a sphere. So I'll change the append mesh here in this case to something like unit sphere here. And we can see that this now makes more sense. So what we can see is that the visualized mesh is independent from the simulation. And this is a benefit because this allows us to change the visualized mesh without having to rerun the simulation. It is worth noting that we can generate our own custom collision shapes. You can see I can change the collision shape to mesh and we can provide one. And we can also have multiple collision shapes for one simulation. And we can do that by going over to the input count and increasing it. But this is a little bit out of the scope of the video that we have for today. So now with our input collision shape set to sphere, let's go ahead and change the mesh that we're viewing here from this sphere to our apples. So what I'm going to do is I'm going to go back to my package management panel, find the Apple FBX, and just drag that into the graph. I'll go ahead and bring back my viewport. And so now I'm going to connect this Apple FBX here to the append mesh 1 input. Not the mesh input, but the append mesh 1. And as soon as I do that, we can now see that the apples have been spawned on our points, and this is looking great. So I can go ahead and rerun the simulation, and we now have our apples falling to the ground and scattering and colliding. Now, scattering things onto a flat surface is extremely useful when creating piles of debris and things like that. However, in our case, we want to fill a crate with our scattered objects. So let's now look at how we can bring the crate and incorporate it into our simulation. So just like the apple, let's go ahead and bring in our crate by going back to package management. And I'm going to use crate 1 here and just bring this into the graph. Now, don't connect the crate to the mesh spawn on point cloud node just yet, because we need to tell our simulation that we want to use the crate first. So we need to tell the simulation node that we want to use our crate as a collision object in the world. And so to do that, I'm going to go to the physics simulate rigid body node, and I'm going to go to this ground category and change the type from plane to mesh. You can also see that we can use a height map, which is pretty cool. But in this case, we're going to use a mesh because we have one here. And so now you can see we have this ground mesh input, and I'm going to connect the crate to the ground mesh. Let's go ahead and click on the output pin from the mesh spawn on point cloud so that we can see what we're doing. And now things look a little bit interesting. You can see that if I go ahead and change the iterations, something is happening here. If I go ahead and just go back a little bit and then just slowly advance through, and we can see that our apples are definitely bouncing off something, but we can't visualize it in the scene yet. And that's because we now need to connect our crate to the mesh input of the mesh spawn on point cloud node. And this input allows us to pass through a mesh so that we can see our collision shape here, this crate that we're using, in addition to the scattered apples, the scattered meshes that we have on our points. Now, either we have really small apples or we have a massive crate, but either way, we should balance this out. And in our case, what I want to do is I actually want to increase the size of the apples. Now, there are two ways to do this. We can choose to either increase the size of the apples after the simulation, or we can increase the size of the rigid bodies. And I want to show you the first way first. So if we go ahead and go to the mesh spawn on point cloud, that's where we're assigning and attaching meshes to our points. If I go ahead and just go to the scale here and just increase this up, let's go ahead and zoom in on our simulation here. What we can see is that our apples are actually intersecting. They're colliding with each other like this. And this is because the simulation has already occurred and the points have already settled. We're just spawning a model representation of these apples onto those points after the simulation. So scaling up the apples after we've run the simulation is not what we want to do in this case. So instead, what we want to do is we want to increase the size of the rigid bodies so that we get a more physically accurate simulation. So to do that, I'm going to go to the physics simulate rigid body node and then go down to the transform settings here, and I'll increase the scale. So you'll notice as I increase the scale, our simulation is changing. We don't have any intersecting apples. And 2 is looking okay, but I think I want to make these a little bit bigger. So let's try something like 2.5. And I'll go ahead and override the maximum here for the node. And that's looking a lot better. So we can very clearly see the apples in the crate, maybe a little bit stylized, but I think that looks good for our use case. Now our crate looks like it could use quite a few more apples. So to increase the apple count, we can increase the amount of points that we're generating from our initial point cloud here. So I'll click on the point cloud shape generator, and I'll just go ahead and increase the points per component to add more points into the simulation. Now notice what's happening here. Every time we increase our points per component, we're actually adding quite a few points to our point cloud. But notice that as I do this, we're not really seeing a large increase of apples. And this is because, like we looked at before, the physics node is removing points that are overlapping, and there just isn't enough space around each of our points to simulate more. So we can see this if I go back to our point cloud here, there's definitely not enough space here. In fact, if I even go back to the simulation and just take the iterations down to 0, we can see there's only enough space for these amount of apples, and we can go back to the transform to see what's going on here, right? So what we could do instead is we could scale up our point cloud using this point cloud transform node to add more space to our points and therefore spawn more apples. So with the point cloud transform output selected, I can use the gizmos here to rotate or scale or translate the point cloud as before. In this case, I'll go ahead and use the scale gizmo, and I'm just going to increase the scale on the y-axis here. Just like that. And so if I go ahead and view the mesh spawn on point cloud node, remember we have our iteration set to 1 on the simulation node. But if I now go ahead and transform this and move this up, you can see that we can get a lot more apples. I can use the R key to switch to the scale gizmo and just increase this here, and we can get many more apples in our simulation. So now if I go and advance the simulation by increasing the iterations, we can see we're filling up this crate with many more apples. So yeah, we can see the point cloud shape generator has about 7 points per component. We might only need about 4. That'll make things a little bit easier. I think that's better. Then, we're transforming our point cloud, then running the simulation, and then spawning our apples onto those points to get something that looks like this. Now, the last thing we're going to cover today is how to wrap up this graph into a single node that you can then use to fill any crate with any object. Now, let's first focus on being able to change the crate mesh. So if I go down here, you can see we have our crate mesh input here. And what I want to do is I want to promote this crate mesh local variable to a graph input. You can see if I just click on my graph here, we can view our local variables, and we have our crate and our apple. And so what I'm going to do is I'm going to right click the crate1 FBX local variable and choose to promote it to an input parameter. So local variables are really useful because it allows us to store and reference information inside of our graph. And this is all private, so we can make adjustments inside of the graph and be able to access those different points throughout the graph, which is really helpful. But because those are private, we can't change the crate mesh if it's a local variable from outside of the graph. So we can expose it and turn the local variable into a graph input. And so now that our crate is a graph input, we can make adjustments to it from outside of this graph, which is going to be really helpful, as you'll see in the future. So let's go ahead and rename this. I'll call it crate mesh. And so now what I can do is I can go ahead and double click the crate mesh, and I can bring in a different mesh. So let's go ahead and bring in crate 2, for example, so that we can fill our new crate with those apples. So now immediately we can see that we have a new problem that we have to take into account. And that is that our second crate is much bigger than the first. And when we're designing a tool that's going to be used to fill any crate with any object, we need to make it so that we can constrain the size of our crate mesh, or at least automatically scale it so that we can get predictable results. And so to do that, we can use a very handy node that's built into InstaMAT called the Mesh Target Scale node. All right, so I'll bring up Quick Search. Let's find the Mesh Target Scale node and bring it in. So the Mesh Target Scale node takes an input mesh, that's the mesh input here, and automatically scales it to fit the size of the target mesh input. So because we designed our simulation to work with the scale of crate 1, let's use crate 1 as the target mesh here so that all of our other crates automatically get scaled to match its size. So I'm going to go back to the package management panel and bring in crate 1 again. And I'll go ahead and connect it to the target mesh input. I'm then going to, let's just go ahead and view our output here. And so now I'll take our crate mesh input. That's the one that's going to be changing, and that's the one that we promoted to a graph input. And I'm going to connect it to the mesh input. So now I'm going to go ahead and borrow these connections here. I'm going to hold Command, you can hold Control on Windows, and just left click and drag to borrow those connections and reroute them so that we're connecting to the output of the mesh target scale node. And there we go. Now we can see, if I go ahead, I'll just go ahead and put F to focus, and I'll just re-simulate by changing the seed here. We can now see that our crate 2 has been scaled to fit the proportions of crate 1. Now, right now you can see it is floating in space, so we can adjust the parameters of the mesh target scale node by clicking on it here and going to the pivot and change it from mesh center to mesh origin. So now you can see the crate is nice and flat on the floor. So now what we can do is I can go to my crate mesh input. I can double click it and I can now change the crate. So let's go ahead and choose something like crate 4. And you can see that even though it's a different crate and it had a different size originally, it still fits the proportions of our target mesh and swaps out gracefully. Our apples are then simulated, and the crate is used as the ground mesh for our simulation so that they collide with it in a way that we expect. So I can change this again. I can go and change this back to, let's use crate 3. I can change this to crate 2 again, go back to crate 1, and things seem to be working really well. So now let's do the same thing for our apples. We're going to promote our apple local variable here to a graph input. Then we're going to use another mesh target scale node to ensure that any object that we choose to fill our crates with have a consistent size so that we can get predictable results for our simulation. So let's go ahead and do that. I'm going to go over to my Apple FBX local variable, right click it and choose to promote to an input parameter. And I'm going to rename it to something like, let's do produce mesh. There we go. Let's use quick search again to bring in another mesh target scale node. And then we'll use the apple as our target mesh so that everything else will scale down to the proportions of the apple. So let's go ahead and bring in the apple. Again, I'll connect it to the target mesh. We can go ahead and bring our viewport back. And then I'm going to connect the produce mesh. This is the one that's going to change with our input to the mesh input. And then I'll just go ahead and connect this to the append mesh 1. So that is the mesh that we're going to be spawning on our simulated points. Now, nothing should have changed here yet because we are comparing apples to apples, but let's now go ahead and change the produce mesh. So again, produce mesh, double click that. I'll go ahead and find another mesh in my package. Click the package option here, and you can see I have my potato, so I'll just go ahead and double click that. And now you can see that we've spawned potato meshes where the apples were. I can go back to my package and let's go ahead and find something like this onion, and I'll go ahead and drag that onto the produce mesh input. And then we can see now we have onions. So as we can see, we can now fill any crate mesh with any produce mesh while keeping the scale of our objects consistent. And therefore we can now fill any crate with any object. Now, to wrap up our entire process here as a single node, we need to create a mesh output. That's the last step in the process. So let's go to the very end of our graph, go to the output here of the mesh spawn on point cloud node, and left click and drag out a connection to bring out quick search, and we'll choose expose output as graph output. So now we're passing all of the mesh information to the output of our graph. Now, if you wanted to export our meshes out of InstaMAT Studio, let's say that you want to process everything here within InstaMAT Studio, and you've assigned a crate mesh and you've assigned some produce, you've scattered it, and you just want to export the geometry out here quickly. What you could do is you could view the last output of the process here, go to the viewport and click on this floppy disk icon to export the viewport scene. Or what you could do is use this curved arrow here in the toolbar and use the image and data output export dialog here. So what you can do, because we've created an output here, if we use the output dialog, the dialog will recognize that we have a mesh output available, and you can use that to export all of the data to files onto disk. But what I'd like to do now is demonstrate our new node's functionality by instancing it into another graph. So I'm just going to save this. I'm going to use Alt or Option S to save everything in my package all at once. And then I'll go back up to the plus button here and create a new element graph. And let's go to the package management panel. We can see we have our crate simulation graph here that we just created, and I can just left click and drag it into the new graph that we just made. Let's go ahead and view the output. And we can see we have our crate and our simulated produce. Let's change the crate mesh. So I'll click on the mesh here and let's go and pick something like, let's do crate 2. There we go. We can see it's updated here. I can change this back to something like crate 1. Excellent. And let's go ahead and change the produce. So I'll go ahead and change this to the apple. And there we go. All right, so just before we finish up this video, I wanted to quickly show you what it's like to use our node that we just created, this new tool, inside of a different application using InstaMAT's integrations. So right now you can see that I have InstaMAT for Blender loaded up here, and I've got a crate here in my scene. I've got this quick scene set up, and let's just say, for example, this is a crate that I modeled here quickly in Blender, and then we also have something like this avocado, which could have been sculpted in here as well. And so what I can now do is use our node that we've created with InstaMAT for Blender to fill up this custom crate with this object. So all I have to do is go to the 2 parameters. These are the 2 exposed graph inputs that we created in InstaMAT. And so I can go ahead and find the crate mesh. So I'll go ahead and select the crate. And then I'll also go ahead and select the produce mesh, which in this case is the avocado. And so now all I have to do is update the instance. Great, so that's done. Now all I'm going to do is import the meshes that InstaMAT has now generated. So I'll go ahead and import the mesh. And so now we can see that InstaMAT has generated those meshes. So let's go ahead and just move this up a little bit, and I'll go ahead and place this where I want it. Maybe I'll just go and hide the other crate and the avocado for a second. But now you can see that this tool we've created has now generated this new geometry. And so I can go ahead and select these different pieces. I can go ahead and remove this one here and customize this any way that I'd like. And so now our tool has saved us so much time. We can continue, creating a whole bunch of crates and a whole bunch of objects filled with different things very easily using the node that we've created. Thanks for watching this introduction to using rigid body physics in InstaMAT Studio. Now, if you'd like to learn more about working with the different nodes in the canvas, as well as other InstaMAT project types like layering and materialize image, be sure to subscribe to our YouTube channel. Here you'll find an ever-expanding library of videos covering the ins and outs of InstaMAT. And also, check out our community forum and Discord server, where you can ask questions, share your creations, and engage with other members of the community. Well, that's it for now. Thanks for watching, and we'll see you in the next video. If you enjoyed this video, drop us a comment below, and don't forget to subscribe. For the latest news about InstaMAT, please visit our website and follow us on Twitter. You can find all the links in the video description below. Thanks for tuning in, and we'll see you in the next one.